In this screencast, we'll continue about talking about universal programs. This is Universal Programs Part 2, so let's remind ourselves of the big picture that we're discussing. So in several previous screencasts, we talked about Godel coding and decoding, essentially the equivalent of modern compilation and reverse compilation. So Godel coder takes an L program and produces a natural number, compiles it into a natural number, whereas Godel decoder takes that natural number and extracts the source, right, of the program. So and the universal programs take those natural numbers compiled by Godel coders, and they either output a number, right, and that's the value of their output variable, y, right, so that's the where they run the program on some given input, or they diverge. Or in other words, so what does it mean? Well, if an operating system executes a program with an infinite loop, the input is not defined. So and the technical term is divergence. So the program's behavior is not defined on a given set of input. So to review our notation, so let's consider n. Let's take n greater than 0, and psi sub un n plus 1 is a function of n plus 1 arguments, and is equal, as we have agreed and defined the notation, to phi of n x1 through xn plus 1. Same. So what does that mean? Psi of u sub n is the value of the output register of the universal program of n arguments, u sub n. That's the nth universal program, when it runs program number xn plus 1. So, well, we take some L program p and compile it into the number of p, a Godel number of p, by this is the Godel coder does that for us. And so that's this value denotes the value of the y register of u sub n, right? The value of y at the terminal snapshot of u sub n. So you or if u sub n never terminates, so the program, for example, p has an infinite loop, then that value is not defined. So what exactly do universal programs do? And so that's the question that we'll consider next. What does u sub n do? So remember, there's a sequence of universal programs, u1, u2, u3, u sub n, and each program can run arbitrary programs of n arguments. So it is given p such that the number of p is y, right? P compiles to y, and that's the value of x sub n plus 1, and some inputs to p. Well, as a matter of fact, n inputs to p, because p must be the program of a program that takes in inputs. Then u sub n extracts the source code instructions, and that instruction happens in sequence, one by one, right? One by one. Then u sub n executes each instruction, and it also keeps track of the state of the program. So, and the state of the program is a mapping of variables to their values. Right? We have talked about it in the previous screencasts. And finally, it runs the instruction counter. So essentially keeps track of which instruction is to be executed next. Right? Although one instruction can be executed at a time, they don't have to be executed consecutively because there are go-to statements. So let's remind ourselves of the variable and label encoding, because we will need these encodings when we talk about how to encode the state of the program. So remember, we define these functions that map the variable to number, right, to the place in the infinite sequence of variables. So the number of y is 1. In that sequence, it's actually given about y, x1, z1, x2, z2, x3, z3, and so forth. And so x1 is 2, the number of z1 is 3, and so forth. So you can watch the previous screencasts to remind yourself of how to do that. But that's a primitive recursive. Both functions are primitive recursive, right? Encode that compute the positions of variables and the positions of labels. So how do we encode states? The state is encoded as a Godel number, or G number. And so remember that G number is just can be thought of as an array of powers of primes. The power of 2, the power of 3, the power of 5, the power of 7, the power of 11, and so forth. So, and the positions within that array of x's, the input variables, are even. And the position of y, which is the output variable, is 1. Okay, and finally the positions of z's, and z's are internal variables of L programs, are odd. It's just a convention that Davis, Wayoker, and Segal adopt in their text. So we will follow the same convention. So we can come up with other encodings of states. So for example, S, for example, the state is y, the value of y is 0, x1 is 2, and z1 is 0, and x2 is 1, and z3 is 0. So how do I encode that state? Well, it's 0 to Z2 is not Z3. All right. Okay. So it's Z1 and Z2. Okay. We'll correct that later. So Z2. All right. So 0, 2, 0, 1, and that's equal to 2 to the 0, 3 to the second, 5 to the 0, and 7 to the first. So 3 to the second times 7 gives us 63. Okay, so let's generalize this example. So suppose that our state is a Godel number, A1, A2, A sub n. So A1 encodes the value of y. Then A sub I, if I is greater than 1 and I is even, so 2 times n, then n is a natural number, then A sub I encodes the value of an input variable, specifically input variable xi divided by 2. And examples will come momentarily. And then for A sub I, such that I is greater than 1 and I is odd, to n plus 1, then okay, let's correct this. Then a sub I encodes the value of an internal variable z. Z specifically sub I minus 1 divided by 2. So, for example, A2 encodes the value of, well, 2 is even, so x 2 divided by 2, x1. And that is true. And then A4 encodes the value of x 4 divided by 2, x2. And then, well, let's play with a couple of more examples. A3 encodes z sub 3 minus 1 divided by 2, which gives us z1. That's the value of z1. And it's A5 encodes the value of z sub 5 minus 1 divided by 2, which is z2. Okay, so here's, let's consider a quick example. Suppose that we have this state in which y is 0, x1 is 2, z1 is 11, x2 is 4, z2 is 31. I'm sorry. So then the g number corresponding to this state is 0, 2, 11, 4, 31. And that is equal to 2 to the 0, 5 to 3 to the second, 5 to the 11th, and then 7 to the 4th. Okay, and then 11 to the 31st. Okay, so let's talk about universality theorem. This is just the first look. We'll continue with this in the next couple of screencasts because it's a pretty involved theorem. It's proved in the third chapter of Computability, Complexity, and Languages, second edition of that book. Great book on computer science, theoretical computer science. So for each n greater than 0, phi of n, x1 through xn, and y is partially computable. So well, what does this theorem give us? Well, it's the essentially will furnish a mathematical proof of the feasibility of operating systems. So so partially computable means that it can be computed by an L program. So we can write an operating system that will take an arbitrary program and run it on its arguments. So that's what this theorem actually shows, or can be an interpretation of this theorem. So modern operating systems and virtual machines, such as Windows, Linux, Java virtual machine, Python virtual machine, Lisp machine, they owe their existence to this theorem. Okay, this is to be continued.